Okay, let's get started. So this week we're going to do the second half of the chapter. So last week we did the sequences part. Now we're going to cover the series part. So firstly, what is a series? So we'll just go through a definition of that. So given a sequence, AN, so this sequence is anything like we covered last week. Okay, so all of those sequences from last week, that's something like AN. Okay, we define the nth partial sum. Okay, so the nth partial sum of the sequence is then S sub n is equal to the sum from n equals 1 to this capital N of A sub n. So the nth partial sum is given the sequence, we take the sum of the first n terms. Okay, that we call the nth partial sum. And we give that the letter there, capital N. Okay, if the limit as capital N goes to infinity of this partial sum exists, then we say that the series converges. Otherwise, the series diverges. So it either converges or otherwise it diverges. Okay, so that's all dependent on this limit here. So given some sort of sequence, as a little n, given that sequence, we can take the sum of the first n terms, whatever that might be. Then when we take the limits of n going to infinity, if that limit exists, we know how to determine that from last year. So if the limit exists, then it converges. Otherwise, if the limit does not exist, for whatever reason it doesn't exist, then it diverges. Okay, so that is how we tell if a series converges or if the series diverges. Okay, now calculating this limit is often very difficult. Okay, so actually calculating it, we're not going to be doing that. For some special cases, we can calculate it, and we'll have a look at some examples with that. But most of the time, for a given sequence, this is far too difficult to calculate. So instead, we use one of these 10 series convergence tests. Okay, so there's 10 of them we'll go through. So given a particular series, you can use one of these tests to tell if it converges or diverges. Okay, so instead, we use some series convergence test. You will see today there's 10 of them to tell if it converges or diverges. Talking needs to stop. Hello? Yeah, that group in the back there, that needs to stop. Okay, so there'll be these 10 tests, and depending on the test, you'll be able to tell if it converges or diverges. For example, you calculate this limit. If easier limit, if the limit is greater than 0, it converges. Otherwise, it diverges. It'll be something like that. Okay, there's 10 of them. You need to know all 10. So number 1, the test for divergence. So these are just the names for them. So that's the name for the test. So given a series, you'll say this series converges by the test for divergence, or diverges using the test for divergence. Right, it's just the name we give for the test. Okay, so what does this do? So if the limit as n goes to infinity of an, so that's our sequence limit, is non-zero. So you calculate the limit of the sequence. We've done that last week. If that is non-zero, then the series diverges. So that's how we do the test for divergence. Okay, otherwise, try a different test. Okay, so a lot of these tests have this little issue here. Not a lot, so a few of them have this issue that calculating this thing, you either know it diverges or you have to try something else. Okay, and we'll see there's two more examples of this. So if the limit is non-zero for whatever value, then it diverges. We know that 100%. If the limit is zero, we need to try something else. It doesn't tell us anything. Okay, so yeah. Anything. Positive number, negative number, 1, -2, anything. But if it's 0, then the test tells us nothing. We need to do something else. Okay, so if the limit is 0, then we can't use this test. And so we must try something else. Okay, so it's just a little thing that you need to keep in mind for this one. Okay, number 2, the geometric series test. You know this one from before. Geometric series test. Okay, so, well, as the name suggests, we have some geometric series. So it will be the sum, n equals 1 to infinity, a r to the n minus 1, right, your normal high school series thing. So this converges if that r there, the ratio is less than 1. So if the absolute value of r there is less than 1, then the series converges. Otherwise, it diverges. So this one, you know, from high school. Okay, number 4, the p-series test. So we did cover this when we did the improper integrals. We had the p-series test for integrals, the 1 over x to the p integral from 1 to infinity. So we have a very similar one for series. Okay, so again, very similar to what we saw for the improper integrals. So we have the sum, n goes from 1 to infinity, of 1 over n to the p. Right, again, very similar. Yeah? What do I call it? 4. No, that's number 3. Thanks. Okay. So again, very similar to what we had with the improper integrals, but now it's instead of the integral of 1 over x, we have the sum of 1 over n. Okay. But it's the same thing. So if p is greater than 1, it converges. If it's less than or equal to 1, it diverges. Okay, it's the same rule as before. So if p is greater than 1, then the series converges. If p, well, the other one, so if it's not greater than 1, it's less than or equal to 1, then the series diverges. Okay, so same rule as we did with the improper integrals. Okay, number 4, the integral test. Okay, so here instead of evaluating the series, we convert it to an integral that is easier to solve. So instead of doing the series, we do the integral, and we'll see if the integral converges, then the series converges. If the integral diverges, then the series diverges. Okay, so a lot of the times the function will be easier to integrate than the series. Okay, so we have the sum, n goes from 1 to infinity, a sub n, okay, with the sequence an. So we define a function f of x such that f of n is a sub n, right? Like we did for the sequences. Okay, now there's a few conditions on this f. Okay, it doesn't work for all the cases. There's 3 things you need to check before doing this test. So number 1, f must be continuous. Okay, if f is not continuous, you cannot use this test. It doesn't work. Number 2, f must be positive. Okay, so if f is positive and then sometimes negative, sometimes positive, you cannot use this test. Okay, it must always be positive. And number 3, f must be decreasing. Okay, not sometimes increasing, sometimes decreasing, always decreasing. So we'll do a little picture on the side of what this should look like. So continuous, it must be one continuous line. Positive, it must have positive y values. And decreasing, it must be decreasing. So the only thing that it can be is this. Okay, so that's our f. Okay, so if the f does not look like that, you cannot use this test. It will not work. Okay, and like I said, if the integral converges, then the series converges. If the integral diverges, the series diverges. So what integral is this? It's the integral from 1 to infinity, f of x dx. Okay, so instead of doing the series from 1 to infinity, you do the integral from 1 to infinity. So if this converges, then that original series also converges. Yeah, and the other way works as well. If it diverges, the original series diverges. Okay, and then just for these 2 integrals, put a little warning there. These are improper integrals. Okay, because it's from 1 to infinity. So all of that stuff we covered last semester with improper integrals, all of that applies here. Okay, remember you have to check the upper bound and then take the limits, and then if the limits exist, all that stuff. So all of that applies for these integrals as well. Okay, number 5, and then we halfway. The comparison test. So depending on where you look, it's either the comparison test or the direct comparison test. Okay, but those are exactly the same. Okay, so if you're looking in the textbook or with the YouTube videos, if the guy says direct comparison test, it's the same thing as the comparison test. So those two are the same thing. It's not like two different tests. Okay, so what do we have? We have two series. So the sum, I'm not going to write the whole n goes from 1 to infinity, but you just add that in. So we have two series, A and B, okay, with positive terms. Okay, so just underline that. Okay, if they don't have positive terms, then this doesn't work. Okay, so you always need to check the little things before using the test. Okay, so we have 0 less than or equal to an, and this is less than or equal to bn. So for every term in the two series, both of them are positive, and a is smaller than b for every term. So as you go through, a1 is less than b1, a2 is less than b2, and so on. Okay, so you need to check that first. Then, okay, if the larger one, the bn, if that converges, then the smaller one will also converge. So if the series with bn converges, right, that's the larger one, bn is larger, then the smaller one also converges. Okay. So the idea on how to use this is an or bn. One of them is unknown. We don't know what it is, right? That's given to us. Then the other one is something that we do know. Okay. For example, let's say we have 1 over n and 1 over n squared. Right, if we go back to the p-series test here, we know that if p is 2, that one converges. So we know that one converges. Then we can compare it to the other one. To see if that one also converges. Okay, and we'll have a look at a lot of examples on Thursday with this. Okay, and in the other case, if the smaller one diverges, then the larger one also diverges. So we swap it. So if an diverges, okay, so the smaller one diverges, then the larger one also diverges. Okay. And again, we'll see a lot of these examples on Thursday. Okay, number 6. Okay, but again, just for this one, just keep in mind what I said. So if the larger one converges, the smaller one converges. If the smaller one diverges, the larger one diverges. Okay, please do not mix them up. Okay, so just make a little note on the side there for that. Okay, number 6, the limit comparison test. Okay, also don't mix up these names. So here we have the comparison test. Here we have the limit comparison test. Okay, those are two different things. Okay, again, we have two series. We have two series, an and bn, like before. Okay, so let's say the an one, we know it. So we know if it converges or diverges. Okay. Another one, bn, this is the one given to us. So we don't know if it converges or diverges. Okay. So an, we know. It converges or diverges, we know that for sure. bn, we don't know. Okay, then if the limit as n goes to infinity of an over bn, okay, so you take the an from the one that we know and the bn from the one that we don't know. So an over bn, we calculate this limit. Let's call it L. Okay, if L is greater than 0, but not infinity, then both converge or both diverge. Yeah. So again, the AN, we know it converges or diverges. We know that for sure. BN, we don't know. Yeah, that's the one we're trying to test. So we take this ratio of the two, calculate the limits, and we get L. If L is positive, so greater than 0, but not infinity, then both of them converge or both of them diverge, okay, depending on the series A. Okay. So if series A converges, then both of them converge. If series A diverges, then both of them diverge. Okay, that's number 7. The alternating series test. Okay. So here, when we say alternating series, we mean like the first term is positive, the second term is negative, third term positive, fourth term negative. It alternates between. So we can write that as the sum. N goes from 1 to infinity, minus 1 to the n. So that will be plus 1, minus 1, plus 1, minus 1, and so on. Bn, where all the bn's are greater than or equal to 0. Okay, so this gives us the alternating positive, negative. Okay, so how do we know if this thing converges or diverges? We have a test. So if, number 1, bn plus 1 is less than or equal to bn, in other words, it must be decreasing. And number 2, the limit as n goes to infinity of bn is 0. Okay, so we check those two things. If it is decreasing and the limit is 0, then it converges. So that's one of the easier ones to check. So you just check that it's decreasing. We know how to do that. I showed you the 3 methods last week. You check the limit to 0. Again, easy to check. If it's decreasing and the limit is 0, we know it converges. Okay. Then number 8, the ratio test. Okay. So here we have a series AN. Okay, so sum 1 to infinity of AN. So how do we use the ratio test? We calculate this limit. So it's the limit as n goes to infinity, absolute value. Very important to include that. AN plus 1 over AN. Okay, so you look at the next term, AN plus 1, divided by the current term, AN. Okay, and you call this L. Okay, so you calculate the limits, you get this value L, and then there are 3 things we get from this L. So number 1, if L is less than 1, okay, not equal to 1, it must be less than 1, then the series is convergent. Yeah, so whatever value you get, like a half or a third or something like that, as long as it's less than 1, then the series is convergent. Number 2, if L is greater than 1, then it is divergent. Yep. And then number 3, If L is equal to 1, then you must try something else. Okay, so after all of the work calculating the limits, if you end up with L equals 1, it means the test fails. Try something else. Okay. Okay, number 9. Also, don't mix this up with this one. Okay. Both of them have these limits with the L, but please, they're two separate things. So for the limit comparison test, L must be positive, less than infinity. Then it's both of them converge or diverge. But for this one, you calculate the limit L, but then you have to look at these three cases. Okay, they're different. Please don't mix them up. Okay, and then number 9, the root test. Okay, so again, we've got some series and 1 to infinity, a sub n. Okay, like the other one, we calculate this particular limit. So we have the limit as n goes to infinity, absolute value of a n to the power 1 over n. Okay, so here we take the nth root, right? Like something to the half is square root, something to the third is cube root. This is the nth root. Sometimes you'll see this as the nth root test, but it's the same thing. So we calculate this mess, we end up with L. Okay, and like before, there are three cases for L. So number 1, if L is less than 1, same as we have above here, then it is convergence. Okay, same as before. If it is greater than 1, it's divergence. And same as before, if L equals 1, you have to try something else. Okay. And then finally, number 10, the telescoping series test. Okay, so this is a very special case of a series. So we have some series with a n, like before. Okay. If we can write the series in the following way, then we know that it is convergent. So if we can write this as the sum from n equals 1 to infinity of bn minus bn plus 1, like that. So instead of an, we write it as bn minus bn plus 1. Okay, so what do we get in this case? So if we can write it like this, let's write out a few terms. So the first term, that will be when n is 1. So we can write that as b1 minus b2. Okay. Then if n is 2, we get b2 minus b3. Okay, plus and so on. And then we can go up to some n. We can write this as bn minus 1 minus bn. And so on. Okay, we can write it like that. Okay, so what's nice about this is that in the first bracket, we have minus B2. In the second bracket, we have plus B2. They're going to cancel. So minus B2 plus B2, they cancel. In the second bracket, we have minus B3. In the third bracket, we're going to have plus B3. They're going to cancel. All the way down to the last term. Yeah, so it cancels all the way through. So if we go up to sum n, that capital N, we're left with the first term, B1, and we're left with that last one there, Bn. And that's going to go all the way through. So therefore, the sum n goes from 1 to infinity an is equal to the limit as this n goes to infinity of b1 minus bn. Okay, so that will be b1 minus the limit as n goes to infinity, bn. Okay. This limit will be some number. Whatever that number is, that is the series value. So we know it converges. So if we can write the series, like this. Okay. Then it is convergent, and we know the series value. Okay. We're going to have a look at an example now. It will be one example, and then I'll show you how we can use the multiple methods. Okay, so one example, I'll show you multiple methods. And like I said last week, you'll get something like this. Then for every method you show, you can get your bonus marks. So if you show it converges or diverges with one method, you get your 5 out of 5 or whatever. If you use 3 methods, you get your 15 out of 5 or whatever it is. Okay. And we'll see with this one, there's a lot of ways of actually solving it. Okay, so you only need to provide one. If you show the others, it's just bonus marks. Okay, so example. Okay, so today we'll do the multiple methods. On Thursday, I'll just show you one method for each of them. Okay, so we have the sum. N goes from 1 to infinity of 1 over n plus 1. Okay, so we have this. So we're just going to go through a couple methods of solving this. So firstly, what you should see is the bottom is factored, right? N times n plus 1. So if you remember back to when we did the integrals, if the bottom is factored, what can we use? Partial fractions, yeah. Okay, so we're going to try use partial fractions on the bottom, and we'll see that this is a telescoping series. Okay, so method 1. Use partial fractions. Yep, and then we'll go through the other ones. Okay, so we're going to use partial fractions on this. So we have 1 over n plus 1 is sum a over n and sum b over n plus 1. Right, we can split it up. I won't go through all the working. You know how to do all of that. That's going to be 1 over n minus 1 over n plus 1. Okay, you all know how to do the partial fractions. Okay, so what do we have for the series? Let's write it out again. So we're going to have the sum n equals 1 to infinity of this 1 over n plus 1 is equal to the sum n goes from 1 to infinity, 1 over n minus 1 over n plus 1. But this has the exact form we need for the telescoping series. right? Bn minus Bn plus 1. So here, Bn is just 1 over n. Okay, so this gives us Bn minus Bn plus 1. Okay, so we've written it in the telescoping series form. So we know it's convergent, and we can actually calculate the value. So the series value is given by, remember what it was? We had the first term minus and then the limits of the sequence. Okay, but the first term, that's just 1. The limit, you can clearly see, is just going to be 0. So this is just 1. Yeah. So the series is convergent, and the series value is 1. Okay, so that's method number 1. Let's have a look at another method. Method number 2. We're going to try compare this to something that we know. Okay, so we're going to make some sort of comparison with this. So let's look at the an term. So this is 1 over n plus 1. Okay, so we have something like that. Now this bottom part, instead of doing the whole partial fractions, let's simplify this out. So n goes inside, so it'll be n squared plus n. Now this n in the denominator there, it's positive, right? Greater than 1, greater than or equal to 1. If I take that n away, does that fraction become smaller or larger? Yeah, take it away. So I take it away. What happens to the fraction? Sorry? No, taking it away. Larger. Right? So here, this will be 1 over n squared. That 1 over n squared is bigger than the other one. Right? You can think of it like a half and a third. Right? The 3 is bigger, so that's going to be smaller. Everyone see what we did there? When we took the n away, this 1 over n squared is larger. Sorry? No. You don't see it. Okay. So if I have 2 is less than 3. Right? Makes sense? What if I do the reciprocal and I look at a half and a third? Then a half is now greater. Okay. So between these two denominators, which one is larger? The n squared or the n squared plus 1? Which one's larger? N squared plus n. That one's bigger. So if that denominator is larger, then the fraction must be smaller. Okay? So again, you can think of it as this one being a third and this one being a half. Right? That first one there, that has a larger denominator, so it must be smaller. Right? Make sense? Yes, no? Yes, okay. Okay, so it's smaller than this. Now, this 1 over n squared, that series, we know it converges. Why? Have a look through your tests. Yeah? P series test. P is 2. Exactly. So here we have the sum. N goes from 1 to infinity. 1 over n squared converges by P series test. Right, we know P is 2. It just has to be larger than 1. So we got 2. Okay, so let's have a look at this test over here. This one over here. Okay. So we've got an is less than bn, right? The 1 over n squared plus n is less than the 1 over n squared. And we know that larger one converges. The bn, the 1 over n squared, it converges. We know that. So what can we say about the an? It's going to converge. Exactly. Okay. So the 1 over n squared, which was larger, that one converges. So the 1 over n squared plus n, which is smaller, must also converge. Okay. And you can say the comparison test or the direct comparison test. Again, those are the same names. Yeah. And just to point out here, see how we did the side working for the 1 over n squared? We used two tests. We used the p-series test to show that the larger one converges, and then we used the comparison test to show that the smaller one converges. So it's not one test for one problem. It's you use a test when you need the test. Okay. So it's not like question 1, you only use this one. Question 2, you only use this one. You could use 2 of them. You could use 3 of them. It's whatever is needed for the problem. Okay. And then just a little warning. If you wanted to use another test, like say the limit, you're right. You look very sad. No, don't be sad yet. When we do Taylor series, then you can be sad. Okay. No, you're not allowed to be sad yet. We still got a few more chapters. Okay, just a warning with this one. If we had to do the limit comparison test, limits. Okay, limit comparison test. What would we need? Okay, have a look in your notes to the limit comparison test. Okay, it was number 6. Okay, so we want to try this one. So what do we need? The AN and the BN. Let's go back up to number 6 here. You can see. Okay, so the AN and the BN. Okay, one of them is known, one of them is not known. What can we use for the one that's known? Just think about what we did in the method 2. The 1 over n squared. Yeah, we can use that one to compare them. Okay, so we're going to try compare the sum n equals 1 to infinity, 1 over n squared plus n. This one we don't know. And the sum n equals 1 to infinity, 1 over n squared. This one we do know. Right? P-series test, we know it converges. Okay, so we've got these two. So what do we need to calculate? Okay, so we got these two, the A and the B. So what do we need to calculate in the next step? Yeah. Okay, so we've got this L, whatever it might be. The limit n goes to infinity, the AN over the BN. So this will be the limit n goes to infinity. What's AN? That's the one we know. Okay, that's the one we know, the 1 over n squared. Over, and then the Bn, that's the 1 over n squared plus n. Okay, so just put a little warning here with these limits. They can be a bit difficult, but all of them we covered last year, right? You got your limit laws, your squeeze theorem, L'Hopital's rule, all of that stuff. So here, just next to the warning, put their limit laws, squeeze theorem, and L'Hopital's rule. So again, for this one, this limits the limit in limit comparison test. You need to know all of your limit stuff from last year. Okay. Also, the other one where it had limits, the ratio test and the root test. Right, those also had the limits. So again, whenever you see limits, limit laws, can you see the red? Is that okay? No. Okay, let me go over in pink here. So limit laws, squeeze theorem, and L'Hopital's rule. Okay. You can see the pink there. Okay. So those things are important. So whenever you have the limits, so limit comparison test, that root test, ratio test, anything with that limit, you might need to know, L'Hopital's rule and all that other stuff. Okay. So in this case, it's not so bad, but it can be bad. Okay, so this is going to be the limits. N goes to infinity. Here we've got a fraction over a fraction. So careful with that. You do the little swap. So it'll be n squared plus n over n squared. That easy enough. That will just be 1. Okay. So it's 1. So what do we know? Do they both converge? What do we know? Okay, so have a look. Limit comparison test. So we got our L values 1. What can we conclude? Yeah, greater than 0. So they both converge. Exactly. So this is greater than 0. So both converge. Yeah. So sorry, this was method 3. So we got method 1, method 2, method 3. So you see, if the question's out of 5, now you got 15 out of 5. Yeah. Or whatever it's out of. Okay. You can try with other things now. So try the integral test. Okay. That's another 5 if you can do that. Also try the ratio test. You can try, but that's going to fail. Okay. So try it out. Get the limit. You'll see the limit value is 1, which means try something else. So, just try it out for practice, but you'll see that's going to fail. The root test, don't try that. That's too much. So just try this one as method 4. Okay. So this one, 4 guaranteed methods you can try. So 20 out of 5. Okay, if you can do all of them. Okay, so that'll be it for today. On Thursday, we'll go through 12 other problems, and I'll only show one method for each, but then for homework, I'll tell you another method you can try. Okay, so at the end of the day, you would have covered every method for every problem. Right, any questions? No. Okay, and then on Thursday, I'll explain the stuff for the quiz 15 as well.